Alright everyone, today we're going to be taking a look at this brand new 2021 2485 16-inch MacBook Pro with the M1 Pro or M1 Max processor that does not turn on after a liquid spill. Now, the particular symptoms this device is exhibiting is no power and no light on the MagSafe charger. Now, we have to understand the diagnostic process on this is really not going to be the same compared to other MagSafe machines. We're not going to diagnose this in the same way. The MagSafe port is basically a USB-C port, so no light on the MagSafe charger is basically going to mean no 20 volts. So it's essentially just going to tell us there's no 20 volts. I want to see what amperage this is taking, so I'm going to go ahead and plug in my regular USB-C port and plug it in to the charger and see what it actually takes. These ports are a little bit funny to deal with, so we have to kind of keep pressure on them, or else it'll want to unplug itself. But it looks like I am going to get 5 volts and around 0.0 amps. It did spike up to, around 1 amp or so that raises my suspicion of a short to ground somewhere, but 5 volts, 0.0. Now, on previous machines, whenever we see 5 volts and 0.0, that raises the suspicion of a short on PP-Bus G3 Hot, or in the case of this board, PP-Bus AON, which is the same thing. So what we are going to go ahead and do is we are going to go ahead and check for a short. We're going to check voltage first on PP-Bus G3 Hot. We have our brand new Fluke 287 multimeter right here, which is so far very, very, very nice to work with. And I'm going to go ahead and measure voltage on PP-Bus G3 Hot, which I presume is going to be these 2 fuses right here, if it's anything like older boards. And I have 12.2 volts. So 12.2 volts means that we have PP-Bus there. That is not the reason. So we're going to have to go through and figure out what's going on here. Now, in the case of liquid damage, I always recommend to do a brief visual inspection of the board to see what's going on. So for the USB-C circuit, we most likely have a missing subvoltage. On these boards, there's several different ones. They're a little bit different from prior boards. We have 3V3, we have a 5 volt, we have 3V8, not 3V3, we have a 5 volt line, and a few others that we need. So I'm going to go ahead and just do a visual inspection on the board and see if there's any corrosion or anything that could point me to what the problem might be. Okay, and this is an 820-02100-11. The -11 number is the revision number, so just looking, we have some like stickiness right there. That's nothing to worry about. Voltage regulator here, that's clean. Another voltage regulator there, clean. That's a PMIC, presumably for the NANDs. That is clean. Everything looks, this board looks pristine on this side just so far. One thing to note that I really do have to give it to Apple, this heatsink is very thick. This is a very good cooling system in my opinion. I think they really stepped up their design as far as the cooling design on these and really did a good job for once on their cooling system, because these are big heat pipes, big heat sinks. So I don't want to take off these shields yet because chances of liquid making it under there is probably slim. Here is a voltage regulator for our NAND. I believe for our NAND. It might be for something else, but either way it's clean. Nothing remarkable there. Everything looks pretty pristine on this side. I don't see anything wrong. So let's go ahead and look at this side. So here is our CD3218. Now this guy right here, this controls our MagSafe port. So this is our MagSafe port controller, just like a CD3217, but there's a few other circuit elements that you notice that are different. We have some MOSFETs and a few other things because the MagSafe port can handle more power than the regular USB-C ports. So it's kind of like a modified USB-C deal, and the circuit does have some similarities to the old MagSafe circuit. Let's go ahead and take a break from here and let's look at our schematic. Now here is our MagSafe port circuitry on this machine right here. We're going to have a look at this. Okay, just a really brief scan over. I'm not going to go on as far as how this exactly works. We have a bidirectional data line right there, but what I do want to point out is this does share DNA from the old MagSafe circuit seen on the MagSafe 2 and MagSafe 1 machines. Let's go ahead and compare this to, let's say, a MagSafe 1 2012 MacBook Pro. Now this circuit here is obviously much less complicated, but it does have some similarities here, okay? Sys1 wire is a bidirectional data line. We kind of saw a very similar thing prior on the other machine, but it does share some similarities, although this is very much a simplified version of what is on that other board. They're totally different circuits, but there is some DNA that carried over. And back to our visual. So this area is unremarkable, so I don't think after a history of liquid damage that there's going to be anything wrong on this area because it's clean. So just because the MagSafe port is not lighting up, I don't think there's going to be an issue with the MagSafe port and circuitry itself. I think it's something central to the board. So this is our new battery charge controller. Again, it's totally clean, so I don't suspect anything wrong there. I'm just going to continue on looking around the whole board. I do have some signs of liquid here, but overall looks alright. So our other USB-C port on this side looks clean. This is our backlight circuit right here. Now this backlight chip is not available, so this is pretty much not available anymore. And another thing to take in consideration to any technicians that may be watching this right here is a shield. Okay, this is a shield. It's actually a little heatsink for some voltage regulators here. You do have to pull the shield off after you're done ultrasonicking it, and it does have Apple's proprietary special black thermal paste, so consider using carbon black for that application. And okay, we have some corrosion, and seemingly this is the only bit of corrosion on our board. So alright, so this, based on what I know about other boards, this looks like Wi-Fi. So this looks like Wi-Fi. Now we're going to take a look at our board view. Big thank you to WizKid on the Bad Caps forum for creating this board view. There's some inaccuracies on this board view, but it does give us kind of an idea of what's going on here. So I can most likely tell that this is going to be our Wi-Fi chip right here. So it looks like Wi-Fi. Switch over so you guys can see what I'm talking about instead of just showing you. This looks like it's UL000, interesting name. And this area all looks like 3v8 AON underscore WLBT, and WLBT stands for basically WLAN and Wi-Fi, and Bluetooth, So this is typically going to go through a current sense resistor right here and PP3V8 AON. Now, PP3V8 AON is a very, very important rail. PP3V8 AON is very much like PP3V42 G3 Hot on older boards, really older boards, or PP3V3 G3H on newer pre-M1 USB-C boards. So this may very well be shorted to ground. If you remember anything about older boards like 2010 through 2015, PP3V3 or PP3V42 G3 Hot is the rail that we need before anything else. And PP3V8 AON is going to be very similar to this, but I believe PP3V8 AON is sourced from PPBus, so we need PPBus first, contrary to the other boards that need 3v42 first, but we need 3v8 before any kind of USB-C communication can take place. So I'm going to suspect, given that history, there's going to be a short to ground caused by one of those capacitors that looks really bad right there. So I'm just going to go ahead and measure PP3v3 AON and see if it's shorted. Not 3v8 AON and see it's shorted. And we could check that right here on this empty current sense resistor. This is just bridging the voltage here. They probably had I can't tell you exactly why they admit those current sensing resistors, but it most likely has something to do with debugging when they're doing factory stuff so they can read current. So we're going to go ahead and check for a short here, and we are going to use our multimeter, of course, black probe on ground, and red probe there, and I have 0.02 ohms. Just to show you guys here, I'm going to move my multimeter in view so everybody watching can see what I'm measuring here, or see what the multimeter measured. All right, we have our meter right here. Okay, it's in view of you guys. You guys can see it, and I'm going to measure again. And that is a dead short to ground. 0.2 ohms, that's pretty much just directly to ground. So we're going to go back over, and we are going to clean this area up and take a look here. So I see corrosion here. Now, I'm not going to worry about our Wi-Fi chip being damaged because our Wi-Fi chip is underfill. Okay, now underfill, given the fact this is underfill, is going to change how we handle this repair as well. But I'm just going to go ahead and clean this up with a Q-tip and alcohol just so I can see better. Okay. And anytime when I'm looking at a capacitor, I like to look and see if there's any way that the internals of the capacitor could have been infiltrated with liquid. Okay, and signs of infiltration on a capacitor is typically damage to its end cap. So if we zoom in on this guy, we can see here that there's one end of it that is just totally gone. Okay, look at this end. All right, if you have a capacitor that looks like this, but it's otherwise just oxidized, you can usually get away with touching those up. Anytime that that cap, that seal is broken on that cap, it's got to go. Same with these two guys right here. So this guy, and this guy all have to go. And I'm willing to bet right here, if we take off these three capacitors, our short is going to go away. Now, I'm not going to bother injecting voltage here because we have visual signs here. I'm just going to get rid of these guys. So I'm going to put a little flux down. The discoloration on the Wi-Fi chip is okay. I'm not too concerned about that. It does bring me some level of concern, but it's not overly concerning. Just changing tips out of my iron here. And we are going to go ahead and get rid of these capacitors here. Now, you may be asking, well, why aren't you using hot air? Well, because this is underfilled, right? And in addition to the underfill surrounding the chip, there's actually underfill inside the chip as well. So if we use hot air here, we could very well float this and cause a lot of damage. So we're not going to do that. We're going to use our iron solely for here. Now, this is kind of the instance where you don't want to use hot air in any way in this area, because you can cause damage there. So if it's up to the point where if you can't replace the capacitor by hand and you would have to use hot air here, just leave the capacitor off if it's a decoupling capacitor, because they really aren't going to make too much of a difference, and it's far less risky to leave it off than it is to actually replace it. Now I'm just going to hold my iron here. We're just going to get it preheated a little bit. Raise my temp up a bit, it's a little bit low. And I should be able to just get these guys out of here. And sometimes if your cap is being really stubborn, like this guy is, he doesn't want to come off, and that's partially because the thermal mass of these boards is just so high. What you can do is kind of act like you're pulling a tooth. So I'm going to try these, see if these tweezers are too big. All right, I'm gripping that cap, I'm just moving it back and forth. There we go. Look at that, took all three off. Perfect. So there's that. Okay, I'd rather use mechanical force than hot air here. And if you're iron, sometimes the iron is just really not good at it, and sometimes it will take a little bit of mechanical force. So I'm going to clean this up. You could tell that the iron is actually having a hard time, and these boards are so much thicker, and that comes in as far as thermal mass there. This is a very thick board. This board has a lot of thermal mass, and it will be able to absorb more heat, so you will have to use a higher temperature on these guys. So we're just going to clean that up, just like that. And let's actually wick it away so it looks nice and clean. And we're going to look into replacing these guys if we can do so safely with our iron. If not, they're good to stay off. The other two caps look fine adjacent. Yeah, this board definitely has a lot of thermal mass. You could really, really tell. I'm also going to go ahead and touch up these resistors here. I might replace one of these resistors, but let's go ahead and check and see if our short is gone first. I'm going to check on my same measuring point here. Okay. And now no more short. So that looks like it was the issue there. Sorry for that loud noise. I just bumped my tray. So I want to clean this up again. I want to determine if it would be wiser to replace this capacitor or just leave it off the board. The two small ones we are probably going to leave off because they really don't affect too much. The big one I would like to put back if needed, or if possible, which it should be. So in the side note, I want to talk a little bit about leaving capacitors off, because I know this video is probably going to attract some new viewers. So what these decoupling capacitors do, we have an already very regulated voltage line, 3V8 AON, that already has very clean power. All right, now when you're bringing a voltage across the board like this, so 3V8 AON is generated on one part of the board, and it's brought over to this part of the board that it powers. All right. sometimes you can get a very small amount of noise that's built up into this line under certain circumstances. Now, on a device like this, the chances of that happening are exceedingly low. All right, but in the event that it does happen, all right, the noise would just basically maybe raise that voltage a little bit up, maybe like lower it a little bit. But in the event it does happen, a capacitor is able to kind of smooth that out, all right, so you don't get any disruptions of any kind. The small ones are normally totally unnecessary. A lot of times the small ones are just for manufacturers to be able to pass FCC compliance, and even then you could probably pass FCC compliance with half of these off the board. Okay, anytime you see like the 3 picofarad and 12 picofarad Wi-Fi desense capacitors, that's all those are for. We almost never put those back because they're totally unnecessary, and you're putting more heat stress on the board putting those back on rather than just leaving them off. So I would like to put the big one on because that is going to be our main smoothing capacitor, but these little guys right here, these probably don't have to be put back on. All right, and this is not sacrificing the reliability of the device in any way, shape, or form by leaving those small ones off. If we leave the big one off, there is a very slight chance that the Wi-Fi might be subjected to more noise under certain circumstances, and that might lead to, let's say, a dropped connection here and there. So we're going to put the big one back on if possible, and it should be just fine. I'm just going to get our value here. First, let's look at our little ones. Let's determine if our little ones need to be put back on. And the little ones do not have to be put back on. Those are 3 and 12 picofarad for Wi-Fi desense. Those are not necessary, but our CL007, our big one, is a 10 microfarad, 10 volt. X5R, that guy should be put back. So that's what we're going to worry about there. And then this one resistor, RL004, looks a little bit odd. That's a 51K. That's going to be a really hard value to find. So I'm going to clean that up, and it should be totally fine. I would not suspect an issue whatsoever with that, as long as it's touched up. But I'm going to go ahead and get this area prepped for soldering new components on, or a new component that we are going to do with our iron solely. So I'm going to put some more flux down. And when I'm soldering a capacitor like this, I'm actually only going to tin one end, or one pad, just like that, okay? So that's going to allow me to be able to put the component back on and use my iron. And I'm going to show you guys how I'm going to do that here. So I'm just cleaning these pads up, getting a little solder on them so they look nice and OEM. I really can't stand when I see stuff from other shops that is just no effort into the quality of the solder joints. It's really aggravating to me, so I always try and do my best on them. There, that's good. Alright, so that should be good. This one resistor is a little bit of concern, so I'm just going to make sure I get enough solder on that end of it. And that should be fine like that. Anything else, these guys look fine. Alright, let's go ahead and harvest the cap off of our donor board, and let's go ahead and put that back on. Alright, we have our cap harvested from a donor board. I'm going to get this guy down here, right here. Alright, now I'm going to show you guys how I solder these. So it might be a little bit hard because of the thermal mass on this board, so I'm going to go up to the max temp of my iron just to make it a little bit easier. Okay, so we're going to line this up. Can be a little bit tricky. Now you may be asking, well, why don't you just use hot tweezers? Well, hot tweezers really don't have the thermal mass for these boards. Okay, if I put a hot tweezer on here, it's not going to work. It's simple as that. So I'm going to hold this guy. It's kind of at an odd angle, right? And it's going to take you some attempts. I mean, it's not the easiest thing to do. And that looks decent, but I kind of want it to sit a little bit better. There, that's perfect, okay? So that side soldered, you can notice our flux is getting really degraded from the heat. That's okay. Okay, now we're going to clean it up. We're going to apply some more flux. We're going to hit that other joint again just because we want to do it with fresh flux, because sometimes the flux, it's too degraded and you can't make a clean joint. Yeah, see that? It just kind of just took it right off. So yeah, that's one of the drawbacks to that. Now, we didn't really rip this pad. It's still connected to the via. You can see it kind of peeled up there a little bit. That's all right. It's going to be totally fine. So we're just going to do this again. And again, soldering a cap like this on a board that has so much thermal mass is a bit challenging, and it's okay if you make a mistake like that. It's totally fine. And we're going to check continuity anyway to make sure that it is still connected to 3V8 AON, which it will be when we're done here. That's good. I'm going to go ahead and pull a different cap off a donor board. Alright, we have our other cap right here. We're going to do the same thing. Sometimes it can help if you're struggling at one position. It can help to move your board a bit. Alright, so the board is kind of sitting slant, which it is kind of half off my bench now because of the size of this board. The component does sit slant. You gotta love engineers sometimes. But anyway, let's get this on here. Again, it's tacked down now. I want more solder. And I want more flux. Come on. I need to have it aligned right. Okay, that looks good. Now that is perfect. I need to have it aligned properly so I can get this side decently, which is also our ground side. See, it's definitely, it doesn't want to really stick on that side because of how high of a thermal mass this board has. So it doesn't want to stick. More flux. And in this case, since we already have it kind of down there, I'm going to lower my temp a little bit. Flux is your friend here. And we're ultrasonicing this board after, so we don't have to worry about any damage or anything from the flux. Come on, get back down here. I'm going to run a jumper to this just in case, because the pad might have been... It just seems like it's a little bit loose there. It doesn't want to sit. So I'm going to run a jumper to this side as well. It just doesn't want to sit down on that pad like I want it to. So I'm going to up my temp again. I'm going to clean my tip really good. And we are going to... Let's do this. I'd really, really hate to use hot air here. Sometimes whenever you have a pad that just doesn't want to accept solder, especially on a corroded board, it can help to scrape a little bit, but I don't want to. Just do it really gently. Just like that. More flux. And more solder. So what I mean about replacing capacitors, sometimes you're just better off leaving them off. Because we don't want to, if we used hot air here, this would not be a problem whatsoever. But again, it just doesn't want to stick down there. Alright, that's it, finally. It's down, so we're going to clean up a little bit of acetone, and we're going to run a wire to the other side just to reinforce that pad. We're also going to check for a short again, because we wouldn't want this to short to ground again. Yeah, see, it just came right off again. Interesting. So now this is making me think, alright, so that pad just totally came off. Not a problem, that's easily correctable. And now in this case, what I'm going to do is just tin this pad again. It just doesn't want to accept solder. So anytime you get a pad like that, and you will encounter these pads, I wouldn't say it's common, but it does happen. Lightly scrape on it, okay? Lightly scrape on it. Just like this. Sometimes pads are stubborn and they just don't want to accept solder. It's a very common pitfall in soldering, and this is how you correct it. We're not digging, okay? We're just moving our tweezers very lightly on that, and then we are going to put some solder here. Alright, now we should be able to get our... We'll grab another capacitor. We should be able to get this in here, no problem now. Just like that. Okay, we have hopefully our final cap that we're going to be taking off a donor board. And again, all this could have been avoided if we used hot air, but again, we don't want to use hot air here, and soldering these guys, especially on a board like this with a soldering iron, is pretty hard when you have this high of a thermal mass. There, and that looks almost there. There. There, that is good like that. Now we're going to go ahead and run a wire from 3V8 WLAN Bluetooth, and that could be found right here. So we're just going to touch this up a little bit. And run a wire to that capacitor. Turn my temp down a little bit because it's still a little bit too hot. Perfect. Now we'll go ahead and use 37 gauge enamel coated jumper wire, so it's not going to short anything. After ultrasonic, we will conformal coat this too. I want to put a bend in it like that so it doesn't touch anything it's not supposed to. And we can just run this right along this little isolation edge here. It's not going to cause any issues. just like this. There, that is nicely soldered. Let's go ahead and pull this off. Now you may be asking, well, why would you put a capacitor there when the pad is ripped? Well, the capacitor is still the capacitor is still in the circuit and connected, okay? There's other vias that go to the Wi-Fi chip. All right, think of the circuit as a whole. You want to have the capacitance at a certain level in that circuit as a whole, and it's not going to make too much of a difference with this wire here versus if the wire was on the pad. So we should be good to go. There's that. And now for the moment of truth, we are going to see if this board turns on now, which it will. I know it will. And then we're going to throw it back in the enclosure. We're going to test Wi-Fi for you guys. You can see it detects Wi-Fi networks. And then we should be good to go after ultrasonic, that is. So let's go ahead and plug in our USB amp meter. That is 20 volts, and it looks like booting current. These boards have really low amperage on boot, but this does look like it is booting. Looks like our heatsink is getting warm, meaning the CPU should be alive. Next up, we're just going to throw it back in the enclosure and see if it boots into an operating system, and mostly if the Wi-Fi works. Alright, board is put back in the enclosure. Now these boards are really hard to assemble, honestly. We're going to go ahead and plug our charger in here, and we're going to see what happens. So first, we're just going to let it boot into the operating system. I have trackpad click. I have 20 volts. I don't think I'll get fan spin on this. That is an Apple logo with a progress bar. So Apple logo with progress bar is very good. And there we go. That is a really nice screen. So this is booted. And now we're just going to go ahead and shut it down. And then we're going to hold our power button down to get into the boot menu. So once it's off, which I think it is. Now it is. I'm going to keep holding. It says continue holding for startup options. Loading startup options. Let it go now. And with any luck, we will have a working Wi-Fi circuit. It's funny how something related to Wi-Fi can stop a device from turning on, but it very much can. So it's going to give us a few options here. It's going to take a minute to load them. Options, continue. It's going to boot into its secondary operating system. There we go. And Wi-Fi. There we go. It brings up the list. Alright, so everything should be good to go here. All Wi-Fi networks are being shown. Ours is that nice 5 bars, so you should be 100% good to go. So this one is fixed. This is going to be our first 2021 that is fully done. We had another one that had a bad screen from liquid damage. They couldn't do anything about that because there's no screens available and no parts available for these. But this is fixed. This is one that is saved from the landfill. And that's it for today. So similar repair like this, if you brought this to Apple, would probably cost with this machine probably in excess of $1,500. This one is out of here for just $479. So if you have a similar one of these machines with liquid damage or any other issue that Apple gave you a high repair quote for, we could definitely help you. So that's it for today, and thank you for watching.